So, should we start?
Yes, I think so.
We have a chairman.
Of course, in this case, there is no need for introduction, so just look at the title and everybody knows him. But please start.
Okay, hi everybody. So, in case somebody doesn't know me, my name is Sandvik. I'm from Boston University and also Chinese Academy of Sciences, Institute of Physics in Beijing. Okay, so thanks to the organizers for inviting me back to ISSP. It's very nice to be here. Unfortunately, I had a very bad cold last week and I haven't quite recovered yet, so I hope that I will not lose my voice or fall asleep, because of the cold in combination with the jet lag. Anyway, so I will talk about deconfined criticality in the JQ model, which is a 2D quantum spin model. And these are my main collaborators in this work, and Bo Wen Zhao, he's actually sitting right there, a student at BU. Xiao Hui was my postdoc. Now she is a faculty member at Beijing Normal University, where Wenan Guo also is, and Wenan is also here, somewhere over there. But there are actually many other collaborators. I will give some introduction and so on, so there will be some older papers referred to as well. Okay, so let me make the main points here in the beginning as a kind of introduction. So what I want to talk about is large-scale quantum Monte Carlo studies of this so-called JQ model, which I will define for you as well. Naoki also introduced it in his talk yesterday. So this is what we call a designer Hamiltonian to study a particular phenomenon, and the phenomenon is the quantum phase transition between the standard Nell antiferromagnet, where you have spin order, and the valence bond solid, where you have a bond order. So these represent singlets forming on the bonds in a pattern like that. So this phase transition supposedly is described by the so-called deconfined quantum critical point, and that's still very controversial, even though it's by now quite an old topic. But there are lots of interesting things going on at this phase transition. Among other things, this valence bond solid has an emergent U1 symmetry. So although, when we draw the state like that, like people always do, it looks like a very boring state, just some singlets forming there, but actually the fluctuations are very exotic here. So if you just draw a pattern here, you don't see the fluctuations, and the fluctuations actually have an emergent U1 symmetry when you go close to the critical point. And that symmetry is associated with a length scale, which is not the normal correlation length. It's actually something we call psi prime, which actually diverges faster than the correlation length. And when we look at this transition, and many groups have been looking at this phase transition, there are some anomalies there, which actually makes some people propose that it's in fact a first order transition. It's not even a continuous phase transition, but actually what we believe is that this second length scale here plays a much more important role than people had anticipated, even in this theory, and actually it causes some unusual finite size scaling behaviors, which we will talk about. So basically we have introduced some phenomenological scaling function which has two length scales in it, and with that it looks like we can explain strange behaviors that we find in this model. Okay, so we are talking about 2D antiferromagnets and quantum phase transitions out of the familiar Nell state. So let me just, to start with, give a simpler example of this kind of phase transition where the Nell order is destroyed, a case where people know basically everything that's going on. So we start from the Heisenberg model, but we make the couplings having this pattern of weak and strong couplings. So you can think of the red ones here as stronger than the blue ones. So now you see that this is a sort of dimerization because each spin belongs to one of the red bonds. So you can think of the red bonds as dimers, the pairs connected by red bonds as dimers. So naturally when that red coupling becomes very strong, you will tend to form singlets on those red bonds. Okay, so as a function of that coupling ratio G, you go from an L antiferromagnet through a critical point into this state, which is not a very exciting state. It's basically a product of singlets on those strong bonds in the limit when G becomes large. Of course, when you come close to this phase transition, you still have a lot of fluctuations, and it's still, interesting to study this critical point, and it has been done a lot using quantum Monte Carlo simulations and other methods. And the transition, as you would expect from just symmetry and dimensionality arguments, it's in the 3D O3 universality class. In some cases, there are also some interesting scaling corrections going on here that people have studied, but basically this is very, very well understood. You go from the null state where you break O3 symmetry to this non-degenerate ground state, and you have a gap to excitations in that state. Okay, so now we want to look at more complicated things. So the reason that we had the kind of transition that we had in the previous slide was exactly because the system is dimerized. So each unit cell has two spins, and you form singlets in those on those dimers. So now we want to do something where we keep one spin per unit cell. So again, we will start with the Heisenberg model on, in this case, on the square lattice with no manual dimerization or anything. But then we add something, and that something we also don't want to break any of the symmetries of the square lattice. And of course, there are many, many things that we could do here. And as a consequence, we could destroy the Nell order and get other types of states. Now, there are two broad families of states that we could get. One is spin liquids, sometimes called resonating valence bond states. Of course, there are many, many kinds of potential spin liquids. The other kind of state that we could get is the valence bond solid that I already mentioned. So when we talk about these non-magnetic states where there's no spin ordering, it's useful to discuss those in terms of singlets, bond singlets, as I already talked about. So the RVB, the generic RVB would be some linear combination of these singlet pairings in such a way that you don't have any kind of long-range order except perhaps topological order, but you would not have any long-range spin or bond order. Now in the other kind of states, the singlets will align, for example, in this columnar fashion, but there are many other ways in which that could happen as well. But the point is that you spontaneously break the symmetry and form some pattern. So for example, in this case, this pattern can form in 4 equivalent ways in the way I drew it, and then you can shift it up one step, or you can rotate it 90 degrees and shift. So it's a 4-fold degenerate state, and of course that strict degeneracy only happens in the thermodynamic limit. On a finite system, the ground state is always some superposition of the four different patterns. Now, so when you just draw the picture again, it looks quite similar to what you would have if you have this static dimerization, if you have created this state by strong and weak couplings. But in fact, those states are very, very different, because the static dimerized case has a unique ground state, but this spontaneous symmetry breaking is associated with degeneracy. So it's quite different. This is the transition into this state again is something that people call beyond Landau-Ginzburg-Wilson. So it's a transition that would not be expected to be continuous within the standard Landau scenario. Okay, and it has been termed the deconfined quantum-critical point. So let me talk a little bit about the field theory description. Now, I'm absolutely no field theorist, so what I'm saying maybe you should take with a grain of salt. I think everything I will be saying here is correct, but it's on a very sort of naive level for a field theorist, I'm sure. So if you just talk about the normal antiferromagnet and for example those dimerized systems that I talked about before, there we can describe what's going on with, for example, the phi-4 theory. There's also other descriptions like the nonlinear sigma model, but they're basically equivalent. So with that, we can describe the low energy physics, and we can describe the phase transition as well. So I'm sure people are familiar with this theory. Okay, but when we want to capture the transition into the VBS, there's nothing in this theory that allows us to do that. We actually need something else. Well, let me talk about this more general thing before. So we cannot describe the VBS pattern, or for example, if we have topological order, we cannot describe it with the phi-4 theory. So here's an example of a topological defect. So when we, even within this kind of description, we can have field configurations that are very singular. So this shows what you may have in imaginary time. So you have some spin configurations that point like that, and in some instant of time they flip to the other direction. So this is what's called a hedgehog. So these kinds of events will not really happen in the null state. The null state does not want to have these very singular configurations. But when you go to the non-magnetic state, the paramagnetic state, and the phase transition into that, that's actually happening by proliferation of these topological defects. So at the critical point, these defects that you can have in the field configurations, they play a very important role. Okay? Now, it turns out that the VBS state corresponds to a condensation of a certain kind of topological defect, actually quadrupled defects in some sense. But this cannot be described just by that theory. So instead, starting actually quite a long time ago, people introduced another description of the antiferromagnet with which it's actually possible by including other terms to describe this kind of state. So there, what they do is they represent the field that we call phi up here by other fields which are actually spinors. So these are two-component complex numbers. And then that should be coupled to a gauge field, a U1 gauge field, and that gauge field can have singular configurations corresponding to monopoles. And the VBS in that language corresponds to condensation of quadrupled monopoles. So 4 monopoles together can form a condensate. So with this description, which again I have not really described, I just try to use some words, they can actually describe the VBS state and the antiferromagnet as well. But during that time, a long time ago, they didn't really discuss what is the nature of the phase transition from the null state to the VBS. Okay? So that remained unknown until this later proposal of deconfined criticality. And that proposal was actually, at least partially, I believe, stimulated by numerics. So I was involved in this work some time ago, where we used an XY, quantum XY model, to which we, which is this term here, to which we added a certain 4-spin term, and actually I should draw a picture, it's easier to see what's going on. If you think of it as hardcore bosons, it's the term which takes a plaquette like that and rotates this by 90 degrees, like that. So this kind of term will actually destroy the XY order in this model, and it will actually when this term is very strong, it will actually give a CDW, checkerboard pattern of bosons and empty sites. But at intermediate strength, it actually gives rise to bond ordering. So this is a picture of the bond strength when you have gone into this kind of phase. Okay, so what one would expect from the Landau kind of argument is that since you break two unrelated symmetry here, this breaks U1 symmetry, and this, in that XY side you break U1 symmetry, and in this state you break a fourfold symmetry, discrete symmetry. Those are not subgroups of each other, so you would expect it to be a first order transition in general. Okay, what we saw in this paper seemed to be a continuous transition, so we could calculate some stiffness which basically captures the XY order and some order parameter of this kind of type, and this rounding here is from finite size. So it's not completely conclusive, but at least it did not look discontinuous to us at that point. Well, I should say that in later work following the deconfined criticality theory, it was actually pretty clear that this eventually is a first order transition, but very weakly so. But in any case, I think I know what happened, because I was at Santa Barbara at the time, and we discussed this with Matthew Fisher, and a little bit later there was a new theory of deconfined quantum criticality, which says that such a transition could in general be continuous. And it was preceded also by some numerical work by Motrunic and Vishnawat, where they actually simulated a 3D classical Heisenberg model, where you also have those topological defects at the transition between the paramagnet and the ferromagnet. If you just do a ferromagnetic classical Heisenberg model, at the transition you have a proliferation of these hedgehog topological defects, so they are actually important for the critical point. But what they did is that they suppressed the topological defects. So during the simulation, they tried to throw away all the configurations that have these topological defects. Okay, at least in certain lattices, they were still able to get a phase transition even without those topological defects. So the order can actually be suppressed by other mechanisms as well. You don't necessarily need topological defects apparently. And then they found that there was a different universality class. So the topological defects, if you have them or not, will actually decide the universality class. So this is a little bit unusual if you just think of the standard wisdom in phase transitions, that the universality class only depends on dimensionality and the order parameter symmetry, right? So here, the symmetries and dimensionalities are exactly the same. What matters also in some cases is what kind of topological defects you have or don't have at the transition. Okay, so then there were some further arguments that led to what we call the theory of deconfined corner criticality. So there the argument was further that the topological defects are dangerously irrelevant. So I will talk much more about what this actually means later, but the point is that at the transition, you can describe the critical point without topological defects. So this is based on what they did here. They suppressed the topological defects. So the theory should not contain topological defects there. But on the other hand, the topological defects are important for describing the VBS. So you need the topological defects if you want to describe the VBS state. So then the argument is that, okay, topological defects are there, but they are actually irrelevant at the transition and relevant in the ordered phase. And that kind of scenario is for an operator which is relevant only in an ordered phase, but not at the transition, is called dangerously irrelevant. So I will talk more about that. Okay, so that was the scenario. Okay, and then they wrote down this kind of field theory based on those spinors that I had talked about before. So, and then they did calculations for that field theory, but the thing is, this kind of field theory you cannot really solve. So what they could do is large n calculations, so n in SUN, so they enhanced the symmetry to SUN, doing n component spinors. And then in the limit of large n, it's almost like a mean field theory, so you can actually solve it, and there the transition is continuous, and it has some exotic features in that limit. And then the proposal or scenario is that this should hold also down to n equals 2. And there's no real calculations supporting that. It's just a conjecture that could be the case. So that's why this has been quite controversial still. I think there's no controversy for large n, but for small n, is it really a continuous transition like that, or is it first order? Do the order parameters jump at some point? You could, within the Landau scenario, you could also have a coexistence phase between them, where you have both AFM and VBS order, or you could have some gap between these phases and the third, maybe a spin liquid phase in between them. But within the Landau picture, you would have to have some fine tuning to make the gap vanish or to make the coexistence phase vanish. So this would be unusual in the Landau scenario, because this is supposed to be generic in this deconfined criticality scenario, which doesn't mean that it's always necessarily a continuous transition, but it should be not require fine-tuning. It should appear generically for some, if you have some model with several parameters, then it should, let's say, often be continuous, not just at some fine-tuned case. Okay, but then, the question was then open that, is this really holding all the way down to n equals 2, or only for very large n? And again, it's not just an issue of is the transition continuous or not, because there are also some exotic features associated with, for example, as I already mentioned, the VBS state itself. It's not a boring state, it actually has an emergent U1 symmetry, there are two divergent lengths, and so on. So there are many interesting aspects here, beyond just the basic question of continuous or first order transition. Okay, but so how can we study this kind of phase transition? So, VBS states people have talked about a long time, but mostly in the context of frustrated quantum spin models. J1, J2 Heisenberg models, and all kinds of other models. And of course, those are very difficult to study numerically because quantum Monte Carlo has sign problems, and as we know, everybody knows here, tensor network calculations, DMRG, we can do something, but we cannot yet really get very conclusive results for most models. So we are doing something else to get VBS order and the VBS transition. So that will be the JQ model. So if you look at the Heisenberg interaction on a bond, it's S dot S, but if I just add a quarter and do 1/4 minus S dot S, that's a singlet projector, right? So basically the Heisenberg interaction is minus a singlet projector on all bonds. So in some sense it likes to have singlets on the bonds, on the nearest neighbor bonds of the lattice, but of course you cannot have singlets on all bonds at the same time, and then the system compromises by making Nell order instead, basically, in the Heisenberg model. Now, what we can do to try to make more singlets in a correlated way, we can make products of these singlet projectors. So if I draw the singlet projector as this red oval here, this is the Heisenberg interaction. If I put a minus sign in front, we want the antiferromagnetic interaction. So then we can make this kind of product, and this is what we call the Q terms. So in the simplest case, we just have define them on the plaquette. So we have a product of two singlet projectors, and we should, when we sum them up, we should also do the ones where the singlets or the projectors are in the horizontal orientation, because we don't want to break any symmetry by hand. So this is the original JQ model with the Heisenberg term and the Q term. And notice that they both come with minus signs when I have defined them in this way. So you can think of both terms as liking singlets, but the second one likes to have the singlets appear in a correlated way, and that's what eventually makes this kind of model have a valence bond solid ground state when Q is large. Actually, if you think about the ring exchange interaction that you get from the Hubbard model, you also get terms like this, but you also get, in that case, the cross terms. So you get that the cyclic exchange has, if you write it in terms of spin of operators, it also has this cross term of S dot S. And in addition, you have the other sign. So the cyclic exchange that you would derive from the Hubbard model really is not this model at all. It has a plus sign and it has another term. So this model is not intended to describe any specific material, but it's intended to study VBS physics and the transition between the Nell state and the VBS. So we call these kinds of models that are designed to study certain phenomena, we call them designer Hamiltonians. So this is a designer Hamiltonian for this kind of physics. And we want to use it to test the deconfined quantum criticality scenario. Okay, so I think this workshop is also a little bit about methods. At least I want to mention what kind of methods we have used, but I will not really go into any details, and I think everybody knows anyway. So we use two techniques. One is finite temperature stochastic series expansion, which is similar to a path integral, but it's based on the series expansion of e to the minus beta h, and sampling all the contributions to traces, to the trace when we write the powers of h in terms of all the bond or plaquette operators, whatever we have in the system. So this is an example of a state alpha and some operators in the Hamiltonian. And now we use the basis of Z components, and then there are spin flipping and diagonal operators. And we can do loop updates in this configuration space, and it's very efficient. So because of the trace, we have periodic time boundaries. So this is like the time direction now, if you will. So in this case, to study quantum criticality, normally we scale the inverse temperature proportional to the system size. To really study the ground state, we could also just choose a large enough beta until we have converged to the ground state. So sometimes we do that. But sometimes to run a little bit faster, we choose beta equals L or 1/2 L or something like that. This would be suitable for if we have a quantum critical point where the dynamic exponent is 1, which it's supposed to be in deconfined criticality, but we can also test that. So we use this kind of method for some of the work, but also we use ground state projection, which in the end is quite similar. So here, this is what we sample in the simulation. So what is this sum of F alpha, F beta? These are basically, this is just a trial state. So we have some states here to the left and the right. Instead of the periodic boundaries we had here, now we have trial states that we project from. And we project with a high power of h, or we can also project with e to the minus beta h. It's not that different. But again, we resolve h to the m into strings of all possible operators that we have in the system. And then we measure things in the middle here. And these trial states are also sampled, so we can actually, in this case, the reason that this works so well here is that we can use trial states written in the valence bond basis, so-called amplitude product states. They're really just superposition of valence bond states with all lengths of the bonds. And then, so this is a valence bond here, and then you see when we do these loop updates, the valence bonds are actually parts of the loops. So we have loops exactly like before. It's just that sometimes the loops are actually belong to the trial state. Now, one advantage of this is that these trial states, they actually conserve some quantum numbers. So for example, they of course are singlets because they are written in the valence bond basis. And also if we use these amplitude product states, which are translationally invariant, they actually have momentum 0, which is the ground state momentum for these systems. So we have basically thrown out a lot of states to start with. If we do finite temperature and we want to reach 0 temperature, then we have to be below the smallest gap of the system, and normally the smallest gap is a triplet gap. Well, in this case, we don't have any triplet states, so the smallest gap we see is the smallest singlet gap. And furthermore here, the smallest gap normally is at pi. Well, here the trial state has 0 momentum, so we don't even see any pi states. So we only see 0 momentum states. So basically, if we really want to see the ground state, this can actually converge faster. If we use e to the minus beta h like we did here, it will converge for a smaller beta. If we use this m here, m has to be of order L times n, which sounds like it can be large, and it can of course, but that's fine. Okay, so I will show results for both these approaches. So if I mention 0 temperature results, it's from this approach, and if I mention finite t's of this approach. In this approach, since we work with these valence bonds, it's actually also a little bit easier to calculate things in a spin rotationally invariant way. So for example, if we want to calculate dimer-dimer correlations, which has 4 spin correlations, if we want to do that in a spin rotationally invariant way, it's actually easier to do it in this approach. Okay, I will not talk about any details of that. Okay, now let's start to talk about the phase transition in the model. Again, we are interested in the VBS and the antiferromagnets. So the first thing is, of course, does the JQ model even have a VBS state? Well, that has been known for a long time now that it does have that. If this Q term is large. Now we need to define our order parameters. So of course the null state, we just use the staggered magnetization. And for the dimer order, we can actually define it in different ways. Here is in a rotational invariant way. As I mentioned, this is easy to do in the valence bond basis. So we just use S dot S, which is the bond strength, if you like, and do the Fourier transform at pi 0 or 0 pi. So we have two components of that order parameter because the bonds can be vertical or horizontal. And then, okay, we can measure the squared order parameters, and I will show some results for those, but it's very useful to look at the Binder cumulants. Okay, here apparently I wrote the Binder cumulant for a case where we only use the Z component. So sometimes in both cases, we just measure the Z component of this, and we can also measure this with Z components. Just do SZ here. It doesn't really matter, but it matters when you put your factors in the Binder cumulants. So you want to define the cumulants in such a way that in an ordered phase, the value goes to 1 with increasing size, and in the disordered phase, or let's say in the phase without that kind of order, it goes to 0. So if we are in the antiferromagnetic phase, then this US should go to 1 with increasing size, and UD should go to 0, and vice versa in the VBS phase. So now, as I mentioned, this kind of work has been going on for more than 10 years, so you can follow the literature and see how the system sizes grow and some of the results evolve and change. These are unpublished results based on this recent work for the Binder cumulants. So now we have gone up to system size L equals 512. So this is done with the SSE at beta proportional to L. So what you can see here is that, okay, this is as a function of J over Q. So when J is large, you should get Nell order, and when J is small, we get VBS order. And you see that if we look at the spin Binder cumulant, you see on this side it's small, and then when the system is big enough, you basically get a step at some point. And the dimer cumulant is close to 1 on that side, and then it has a step and becomes small. And you can see how this step becomes sharper as I increase the system size, which is of course what you would expect if you have a continuous transition. Eventually it should be a step function. Okay, if you have a first order transition, normally you should have a negative dip in the Binder cumulant somewhere, which we don't see. Now, at the very end of my talk, I may mention some other case where we actually have first order transitions without dips in the Binder cumulant, but that's a slightly different story. In any case, this looks like a continuous transition, at least if you look superficial at this. Now, by looking at these cumulants, close to the transition, we can actually basically determine also critical exponents. So I will show some results for that. So we can look at crossing points. So you see here, I have system sizes that are powers of 2. So if we can look, for example, at the crossing between system sizes L and 2L and follow how those crossing points move, then we can extract the critical point. But we can also look at crossing points for a given system size between this cumulant and that cumulant. I didn't throw them in the same graph here, but you can imagine that they will also cross each other close to the critical point, and that crossing point will also drift to the critical point. Now, the slope of the Binder cumulant is actually related to the critical exponent nu, so I will show some results of that as well. But before I show our most recent results and discuss what we really think is going on in this system, let me talk a little bit about this anomalous scaling behavior that people have known about also for quite a long time, and which has led some people to propose that the transition is actually first order. So this first order scenario has been explored and advocated by several people. So the main argument actually has to do with the so-called winding number. So I don't know if everybody is familiar with the winding number, but if you look at some kind of path integral pictures, and for example you look at a boson system, you have a path and the bosons can move in imaginary time, and if you have a periodic system they can also wind around the system, right? So that if you count how many times bosons wind around the system during the whole time propagation, that's the winding number. And the winding number in the space direction, but you also have a winding number in the time direction, which is basically counting the word lines in the system. And those are actually related to physical quantities. So in the boson system, the spatial winding number is related to the superfluid stiffness, and the temporal winding number is related to the compressibility. In the case of the spin system, if you take the squared winding number, it has x, y, and z, x, y, and tau components. So these are the lattice directions, and this is the time direction. And the first two here are directly related to the spin stiffness, which is like the helicity modulus of the spin system. And the second term is related to the uniform magnetic susceptibilities. And there are some factors here, as you can see. So now, if we have a quantum phase transition with dynamic exponent 1, and if we let beta be proportional to L, which is the way to scale beta if you do simulations and you want to, and you're sure that you have that kind of dynamic exponent, then you see then we know that the spin stiffness should scale as 1 over L. I will comment a little bit more about this. This is just a standard scaling law for the stiffness. And the susceptibility should also scale the same way. So if you put that in here, you will see that the winding number squared, as defined here, should actually be size independent if the system size is big enough. So this looks like it should be a good test for z equals 1 quantum criticality. So already in this paper by Uwe Wiese's group here, they found that the winding number actually does not seem to converge to a constant as a function of increasing L. So you would expect in the conventional scenario that, okay, maybe it has some size dependence, but then eventually it should flatten out and become constant. But here it looks almost like it diverges linearly. And why would it diverge linearly? In what scenario would that be? Well, if the transition is of first order, then at the transition you have coexistence of the ordered and disordered states, or let's say magnetic and non-magnetic phase. And the antiferromagnetic component of the state would actually have a stiffness, meaning that rho s should be constant and the susceptibility should be constant. So then the winding number squared itself should actually diverge linearly as a reflection of the coexistence state at the first order transition. So they proposed that actually the transition is first order. And there is similar arguments made by these people here in several different papers. Okay, so I wanted to take a closer look at that at some point. So I did bigger sizes than what they have done, and also smaller error bars. And I did not really, in the end, think that it looked like a linear divergence, which is what you should have if it's first order. It was more like a logarithmic divergence, or a small power, power less than 1. But here in one graph I showed that it was consistent with the log. Well, it's sort of consistent with the log, but it's a little bit better consistent with a small power. But at least in this paper I proposed that it could actually be a log correction. So that would mean that it's still a continuous transition, but there's some anomalies there, maybe some marginal operator that is normally what causes logarithm, something that we don't understand. Okay, but then other people, including people here, Kawashima and Harada and others, I think probably several people in the room here were involved in this paper. So they looked at data collapse to try to extract the critical exponents, and they noticed that if you use different system sizes in your data collapse, the exponents change. And of course, I mean, we all know that the exponents will have some finite size dependence because there are corrections to scaling. So that in itself is not unusual. But here it was like this was like out of control size dependence in some sense. So this on this side here, I think this curves here, for example. Okay, so they also did SUN versions of the JQ model and also looked at the honeycomb model. But let me just focus on this graph here, which is for SU2. I think one is honeycomb and one is square lattice. But in any case, it looks like this 1 over nu as a function of the largest system in the data collapse. It's not even clear if it converges. And this is the anomalous, the anomalous dimension. I think this the scaling dimension that we sometimes call delta of the spin order parameter. I think maybe spin or diameter. Both of them, yeah, both of them. So if that goes below 1, I think it's bad news because that means that the exponent eta is negative, which it cannot be in the conventional scenario. So this was a little bit alarming that there's so much size dependence. Now we did more work a couple of years ago where we analyzed the data in a different way. Instead of doing scaling collapse, we did this L2L crossing points. And we can also extract 1 over nu from that, from the slope of the bind accumulant at the crossing point. And this is what we get for 1 over nu. So indeed, it changes a lot with system size, but this way of doing it should be very systematic, and in scaling theory, you do expect that this size dependence is governed by the exponent, correction exponent omega. So it just may be that the exponent omega is pretty small here. I think it's around 1/2 or something here. But it does seem to extrapolate to something like 2.2, which may also be consistent with this. It's just that they didn't graph it in that way and analyze it in that way. So from our point of view, okay, there are strong corrections, but it doesn't look like it's a first order transition. Actually, if this is first order, you can also make some arguments what nu should go to. So if you take a classical phase transition in d dimensions, a classical conventional transition, nu should actually be equal to 1 over d. So 1 over nu should go to dimensionality d. Okay, now if we are in 2 plus 1 dimensions, you may expect that maybe it should go to 3 then. But actually one can also argue that it should go to 4 because the dynamic exponent of the coexistence state is actually 2. So, you may be in sort of 4 dimensions effectively. So, whether 3 or 4, okay, maybe it could go to 3. I mean, this is definitely a good fit and consistent with that, but okay, somebody may say, well, it really accelerates here and eventually, but it doesn't really go to 4, I think. Well, so there were some other funny things too that we had also noticed before, but here it was seen more clearly because the sizes are bigger. If we look at the crossing points of the bind accumulants, so these are again when we do the bind accumulant for 2 different system sizes. This was just for the spin order parameters, you remember that the Binder cumulants look like that. So if we look at this crossing point, call that G star, and we can call that, this was actually the Binder ratio, not the cumulant, but it's almost the same. So if you look at the crossing point for system sizes L and 2L, this was the slope at the crossing point, and this is the vertical value of the crossing point, so it's the size-dependent critical point, if you will. You see that it has a very strange non-monotonic behavior. So one can fit this, with two corrections, but it's not very reliable to do some analysis with two corrections. But in any case, you can, and you get something like 0.045 for the critical point. And this is the actual value of the cumulant itself. So you see that, well, one message of this paper was that there are actually lots of corrections here. And in addition to corrections, we have something unusual which was introduced in this paper, but which I will get to soon. So anyway, so because of these and many other works that I have not mentioned, they have somehow formed two different competing scenarios for what this phase transition really is, what is the nature of the transition. So the first scenario would be that actually the transition is weakly first order. So all these strange things that we are seeing, for example, in the spin stiffness, the winding numbers, and also these changing exponents, it's a sort of precursor to what people call runaway RG flow, meaning we are maybe close to some critical point, but eventually the flow runs away to some first order transition. So that had been proposed early on, based on these things. But in more recent years, the people who actually proposed deconfined monocriticality, they themselves seem to have given up on their own theory, because now they also seem to say that it should be a first order transition. And what they argue is that there is actually a deconfined critical point, but we can never reach it because it may not be in 2+1 dimensional space. It may be in some fractional dimension somewhere that we cannot reach, or it may exist in the complex plane, meaning that we need some complex couplings to study this model, and it would be described by what people call a non-unitary conformal field theory. So Sentil and Subisachdev and others seem quite convinced now that this is what it is. So, for example, it's discussed in this paper. Well, so even then, it doesn't really mean that the whole deconfined criticality scenario is dead. It just means that, okay, eventually the transition is first order, but we already know from all the numerics that has been done that there's a very large length scale of deconfinement. So I haven't really talked about the deconfinement, but what does it mean? Well, if you think of the VBS, the ground state has all the spins paired up in these valence bonds, and if you break a valence bond, then so let's say you have these valence bonds here. Now let me excite the system into a triplet. I break this valence bond. Then these two members of the triplet, they can separate. But when they separate, you form what's called a confining string in the VBS background. So there's something similar to what you have in quarks, between quarks, something that causes a linear potential between them and keep them bound. But eventually, when you approach the critical point, the VBS fluctuates more and more, and the confining potential becomes weaker and weaker. So eventually, you get deconfinement at the critical point. That's why this is called a deconfined critical point. Now, if the transition is first order, it means that the spin-ons, strictly speaking, don't unbind completely, but we know that the length scale must be very long, probably hundreds or at least hundreds or thousands of lattice spacings. So in practice, that doesn't really matter. It's still essentially deconfined spin-ons, even if eventually there's a very weak discontinuity at the transition. So for example, we have done a lot of work on the spin dynamics, and I will show you in the next slide that we have a very good agreement with the dynamical predictions of some of the field theories. And also we have done thermodynamics, and we can describe the critical point as a gas of deconfined spin-ons. We can get the correct power laws and even prefactors in thermodynamic quantities like the specific heat. So for example, also in work with Marasuva, who is, I think, somewhere here, he's sitting there, we also could confirm that there are actually 4 gapless points in the Brillouin zone. So in an antiferromagnet, we have a gapless excitations if we use the original Brillouin zone at 0, 0 and pi pi. At the deconfined critical point, we get 2 additional gapless points. Okay, so it could be, if the transition is very weakly first order, that there are very small gaps at these points. But if they are very small, then in practice, who cares? So, but of course, still, there's a second scenario that the transition truly is continuous, and that these scaling behaviors that we see that seem very mysterious, they actually are some inherent exciting aspect of deconfined criticality. And what we believe is that the anomalous scaling actually reflects the fact that there are 2 divergent length scales in the system, which has been clear from the beginning, but people have basically dismissed the second length scale as something boring that we don't need to care about. But we think that we have to care about that, and I hope I can convince you that this is true. So that means that there's actually some new physics beyond the deconfined criticality proposal here. So I do have 2 hours today, right?
Right.
Yeah.
Yes, 1 hour to go.
Yeah, good. I may not need exactly 1 hour, but let's see. So let me show one slide from a recent paper where we have looked at the dynamic signatures of deconfined criticality. So this is a paper with many authors, so you probably recognize some of the names. Some of them are field theorists, and some of them are more numerically inclined people. So here we looked at a slightly different version of the JQ model, which is a planar version where well, it's also what we call the JQ3 model, because we want to get a strong VBS. But the Heisenberg term is also isotropic, anisotropic, sorry. So Pij is again the singlet projector, but now we add some SZ, so it becomes, actually maybe there should be a minus sign here, because it should in the end be XY-like. Oh yeah, it's a minus sign there, so we have subtracted some SZ, so the Heisenberg term is now XY-like, so we call it the planar JQ model. Okay, there was some reason why we looked at that one, but let me not. It's actually richer, because you have, when we look at the dynamics, we have the X, Y, and Z components will be different, and in the field theory, there's some predictions for both of them, how they will differ and so on. So we looked at that, but let me not get into that here. Anyway, so how do we study the spin dynamics? So we calculate the dynamic spin structure factor, which is basically what's measured in neutron scattering. It's the neutron scattering cross section, basically proportional to that. So it's just this, space-time Fourier transform of the spin correlation function. Okay, so of course we cannot calculate dynamics directly with QMC, but we can calculate the imaginary time correlation function, and we can use some analytic continuation method to continue to real frequency. So that's what we have done. That would be a whole other talk to talk about how we do that. But in any case, what we do is we compare our result with some basically rather simple mean field treatments of the field theories. The thing is, I showed you at least an equation what this so-called CP n-1 field theory is, which is the original theory of deconfined criticality. But now, field theorists are very excited about these kinds of critical points because they predict dualities, meaning that there are actually other field theories that look quite different, but in the end they describe exactly the same physics. So now even for deconfined criticality, you can actually choose many different field theories that should give the correct description. But since the field theories are very hard to deal with, you need to make some approximation. And when you make approximations, all these dual field theories will give different results at the mean field level, for example. So it turned out that what we needed to do, or Ashwin and Ichon Yo mainly, what they did was basically look at our numerical result and then pick the field theory which has the best description at the mean field level. And the best description is given by basically a fourth flavor fermionic theory. But why four flavors? Well, because we need the four gapless points built in from the beginning. And basically it's this kind of pi flux state. So if you just take this, it's actually quite a simple thing. If you just take electrons, 3 electrons on the square lattice, and you put a vector potential such that you have a pi flux on each plaquette, then you actually get these 4 Dirac points, and that should basically be the mean field description of deconfined quantum criticality. So it's really quite a simple thing. And the result of that mean field calculation is here. So this is in some path in the Brillouin zone. It shows S of Q and omega. So the lower bound is the dispersed spin-on dispersion relation, basically. And since you have, these are spin-1 excitations, so if you excite a spin-1, you have 2 spin-ons, and that's why you get the continuum, because at each momentum you can combine the moment of 2 spin-ons in different ways, and you get a whole band of energies. Well, this is what we get in our calculation with QMC and numerical analytic continuation. And the agreement is not perfect. This is also mean field, so it should not be perfect. But what's really remarkable is that this is the dispersion relation of this pi flux state. And this is what actually we saw initially, but that, we tried to fit the dispersion, but then we realized we don't even have to do any fit because it looks like it has this very simple form. And then these guys said, oh, that's the dispersion of the pi flux state on the square lattice. So then, they did the full calculation and everything seems to agree quite well. Now, the thing is here we use this planar JQ model, which has some value of this delta. Delta is a half, actually. And at that point, when we did calculations for different deltas, we know that if we make it very, very planar, so we go all the way to delta equals 1, the transition actually is first order. We can see that clearly. But at delta equals 1/2, it looked like it's continuous. Well, in later work now we can actually see that at delta equals 1/2, it's actually the transition is actually still very weakly first order. So this actually is deconfined criticality in a system that has a weak first order transition. So you can see that it doesn't matter because the gap at pi 0, which is the new gapless point that you have in this deconfined criticality, which you don't have in a quantum antiferromagnet, not even at the critical point, it's apparently so small that for all practical purposes we can probably neglect it. So even if the transition in general in deconfined criticality is very weakly first order, all this kind of phenomenology is still completely valid. We basically still have a deconfinement on large length scales and so on. Okay, but we believe that in addition to that, the transition really is first order in some cases. As I mentioned, in this case, we think that it's actually first order for large delta, and probably when delta becomes very small, it's continuous. And in the isotropic case, it should be continuous. Okay, now let me start to discuss this dangerously relevant perturbation. What does that mean? And that is related to the emergent U1 symmetry, which is a property of the VBS order parameter. So let's talk about that. So we have these two components, dx and dy, that we can measure, for example, in our simulations. So now to visualize what it means, if you have a dx order, you can think of the singlets forming horizontally, but you can have that in two different ways. So you see, this way, if I shift it by one step, you get that one. Now, if you have y order, then it's like that, and you can also shift it. Then you have that kind of pattern. So these are four equivalent patterns that you can have, and we can represent them in 2 dimensions by an angle, as you will see here. I will put in some axes in a moment. So this is angle 0, 90 degrees, 180, 270. Why is it convenient to do that? Well, you also have the possibility of plaquette ordering. So a plaquette singlet you can think of as a superposition of vertical and horizontal bonds. So if you measure this dx and dy, so here of course in this state you only have dx, and it's positive the way I defined it here. Dx is negative and dy is 0. In a plaquette state, since you have both vertical and horizontal bonds, you have both dx and dy at the same time. So this would be here, and then you have 4 equivalent plaquette states as well. And now, if you think of fluctuations, if you have a small system, for example, it can always fluctuate from one of the realizations to another one. So let's say you start here, and then you just start to flip some bonds. It's a bit hard to see because I didn't include a very big chunk here. But you can go from here to here by just flipping bond pairs. So this one and that one are adjacent to each other, and you can see, of course, if you flip and fluctuate this pair here, you get that one. So it's natural that this one is between these two and this one is between those two. So one can think of these as being represented by an angle in this plane here. Okay. And that also means that you can have anything in between. If you have a big system and you just start from this realization and just flip a few bonds, you will move a little bit to the right or the left, depending on how you flip your bond pairs. So what we can do in simulations is, you take a Monte Carlo configuration, and then you can measure dx and dy, and then you can collect a histogram. Now this is, you may think, a little bit strange, because if you collect your measurements in a histogram, that's not really a normal quantum mechanical expectation value that you are calculating. You are doing something else. But still, that kind of histogram will reflect what's going on in the quantum system, so it's still a valid way of investigating symmetry properties, even if what you are doing is not really computing a true expectation value. So if we want to check in our simulation if we have a columnar or plaquette state, then we should be able to see that by collecting these histograms. So in the theory of deconfined criticality, it actually doesn't tell you that it has to be that the VBS has to be a columnar VBS. It actually could also be a plaquette state. So the critical point should be the same regardless. Okay, so of course this I just drew some dots here corresponding to the columnar or plaquette state. So when we do a simulation on a finite system, we don't break the symmetry by hand, so we should see 4 blobs here, but of course the blobs will have some shape, and since we are able to actually fluctuate between the blobs, there must be some weight in between here too, and you can think of them as domain walls. So if you want to go from this state here to that state here, you have to actually create a domain wall, and the domain wall can expand and eventually take you from one to another. So the domain wall states will cause some weight in the histogram between the blobs here. But basically by looking at where the blobs are located, you should be able to see if it's a columnar or a plaquette state. Okay, so what do we get? So I should have put the graph here, but in my first paper on this model, where I looked at this in the JQ model at j equals 0, so it's just the Q term. It actually looked just like a circle like that. And the same thing basically was seen by Kawashima and his student in a different kind of model, which was also in a VBS state. So this was in the VBS state. We could not tell, is it a columnar state or plaquette state, because it just looks like a circle. And initially that was a bit mysterious, at least to people who did not appreciate the deconfined criticality scenario, because actually in deconfined criticality you are supposed to have an emergent U1 symmetry. So if the histogram looks like a circle, it's actually good news because it reflects the emergent U1 symmetry. But when I would show it to some people, they will say, oh, this means that it's a spin liquid or something. But the fact that you have a radius means that you definitely have an amplitude of the VBS order. It just has not decided is it a plaquette or columnar state yet. So anyway, to discuss that a bit or investigate that a bit more carefully in our joint work with Kawashima and GLO, who was later a postdoc here, and now he's a professor in Fudan University in Shanghai, we studied the JQ3 model, which has a stronger VBS than the JQ2 model. So in that one, you can actually really see that it's a columnar state. So this is what we saw in the JQ3 model, where we don't have any Heisenberg term at all. Then you see for a very small system with L equals 12, you see these 4 blobs here. So the blobs are really located as they should be in a columnar state, and you can also see that you have some weight in between because the system can easily fluctuate between all these 4 degenerate states. And so you do have some configurations that are plaquette-like as well. If you look at those configurations, they look like they have plaquette order. Okay, but then if we go to a bigger system, you see that those 4 blobs become much more pronounced, and eventually, you know, if we go to infinite size, they will just be delta functions. Okay, so how about the JQ2 model, which I drew a sketch of here? So this is, in later work, I did the JQ2 model on larger lattices, and here you see at L equals 64, it looks very circular, and this is again when there's no J term at all, so it's as deep as you can go inside the VBS. So you see that this circle has a radius, which means that the VBS has some amplitude, but it has not formed these blobs yet, which is a reflection of the emergent U1 symmetry. You can see that it's not completely uniform, and that's because the sampling is a bit slow, so you have to sample a very long time, many, thousands of CPU hours to get a smooth histogram. And for L equals 128, I was never able to get a whole nice circle. But what you can do, since you know that you have certain symmetries here, you can do averaging over all the symmetry operations of the histogram. So then you can see that the angular, if you sum up all the weight for a given angle, you can see that you actually have these oscillations here. So there's even here a little bit of columnar modulation, but it's very weak. But it increases with the system size. Okay, so this is basically the evidence of emergent U1 symmetry, and now I want to discuss that a little bit more, and how that is related to what's called dangerously irrelevant perturbations. So in deconfined criticality, we have a correlation length, as we always have at continuous phase transitions. You can think of the spin-spin correlation function, for example, as having some correlation length associated with it. But then there's a length scale of this U1 symmetry. And what does that mean? So basically, if we look at those pictures in the previous slide, you can think of you see here, we have 4 blobs, but they're not very small. The blobs are much smaller here. And here we have this almost circular distribution, but as we increase the system size, you get more pronounced angular fluctuations. So if you follow this as a function of system size very carefully, you will be able to extract a length scale where you basically go from circular to 4-fold symmetric. You can define that crossover in some quantitative way, and that will basically, that length scale will actually diverge with a different exponent than psi. And that exponent, which we call nu prime, is actually larger than nu, because it diverges faster. So this is something which is also known in many classical systems. For example, the 3D classical clock models. So in a clock model is basically an XY model that you perturb with a potential. So each spin sits in a potential which has a q-fold symmetry. Here I show q equals 6. You can also actually go to the extreme case, h goes to infinity, where you really restrict the angles just to a certain number of possibilities. So q equals 6 here. So that's what we call the hard clock model, and the soft clock model is if you just add a potential. So in this case too, you can see something very similar to what we see in deconfined criticality. And this is the context where this term dangerously irrelevant was first introduced. I think these people did not introduce the term. I think it was introduced by Fisher in some later paper. But basically what it means is that if you take the XY model, which has a critical point, and this is in 3 dimensions, and then you add this kind of term here, it actually does not change the critical exponents of the transition. You still have a phase transition, the exponents are exactly the same as before. So that means that this perturbation is irrelevant at the critical point. But clearly the ordered state is different, because the ordered state of the XY model breaks U1 symmetry, but this model breaks ZQ symmetry. It breaks this clock discrete symmetry. And that kind of discrete symmetry breaking, you don't have the Goldstone modes and things like that. So it's actually a very different state. So that means that this perturbation is relevant in the ordered phase. So once you go infinitesimally into the ordered state, eventually it becomes relevant for example, a big enough system size. So that's called dangerously irrelevant. Does not change the critical point, but it changes the ordered state. Okay, so here is an RG flow diagram, actually from again from work done here by Kubo-san and Kawashima and others. So this is actually still partially controversial, even though the phenomenon has been known for a long time. But quantitatively, to describe this kind of RG flow, it's still actually a little bit open how to do it. But so they have a very nice paper where they draw this diagram here. So, but what is this lambda? Well, when you do RG, this clock perturbation will change. So here I call it h, but you can think of lambda as the coarse-grained h. So when you do RG and you sit at the critical point, so you flow to the 3dxy critical point, it should be irrelevant, so that means this lambda has to vanish. Okay, on coarse graining, the effective field vanishes. Okay, if you are at high temperatures in the paramagnetic phase, then you flow to the point P. If you have no clock perturbation, then eventually in the ordered state you flow to this point, which is the U1 symmetry breaking Nambu-Goldstone fixed point. But then with the clock term in the ordered state, you actually flow eventually to a different point, which is this ZQ symmetry breaking point. And so the flow is very interesting if you are in the ordered phase but close to the critical point. Then you go almost to the critical point, but then the system will sense, oh, it's ordered, so it will start to flow towards the Nambu-Goldstone fixed point. But before it gets there, it will actually realize, oh, I'm actually not supposed to break U1 symmetry. I'm actually breaking ZQ symmetry, and then it flows there. So this has been qualitatively understood that this is what happens. But quantitatively, how to actually describe this flow is still a little bit open. Well, this paper went a long way to understand it. And we have some later paper which I will actually talk about on the symposium on Monday. Right? I will talk about our recent work to understand the clock model, which is intended to better basically motivate what we are doing for deconfined criticality. Anyway, so the important point is that if you think of increasing system size, then this crossover to the ZQ happens on some length scale that we call psi prime. And we can observe this in simulation. So I will give a little bit preview maybe of what I will do on Monday here today, but not that much. But only what I need to convey what this length scale is and how we look at that at the deconfined critical point. Okay, but let's say we do a Monte Carlo simulation of this clock model. So now it looks like the XY model, but the angles can really only take these clock angles. By the way, for this scenario of dangerously irrelevant operator to be correct, the number of clock angles has to be 4 or larger. So 6 is often looked at because the exponents are somehow have values that make it relatively easy to see what's going on. Okay, so if we do a simulation, we can calculate the X and Y magnetization by just summing up all the classical spin cosines and sines. So these are the global X and Y magnetization components. And then we can just use arc cosine to get a global angle that we call theta for a given configuration in the simulation. So we actually did this also with Logie and Leon Valens well, more than 10 years ago now, to attempt to understand what's going on. And I think we understood some things, but we got some things a bit wrong. But anyway, these are some histograms. So you see, these are simulations below TC for 8 states and a small system size. So you see that this basically the scale is such that the 1 is the maximum here. So you see, so the radius here is almost 1, which means that you are already at almost maximal magnitude of the magnetization in the model. But even though you have only 8 clock angles in this coarse-grained angle, you don't see any hint of the clock aspect, right? So this is the angular distribution. It's basically just noisy flat. But when you go to bigger system size, you see 8, not really blobs, but okay, there's some very elongated blobs, and you see the angular distribution here. So now you can again see that when you go from L equals 4 to 32, something happens. So somewhere in between, there's some length scale that characterizes the crossover. So we can study that by studying what we call the angular order parameter, which you can base on this histogram. So you take this angular distribution, which is what I plot here, and integrate it with cosine q theta, where theta is this global angle. So if you get a circular histogram here, this will be 0, and if it has this q-fold symmetry, it will be non-zero. So by looking at the finite size scaling of this quantity, we can actually extract the length scale psi. So now in this recent paper that we did with Ben-An Go and Wei Xiao, which I will talk about on Tuesday, we did this in a slightly new way. So we used this quantity phi q, which reflects the dangerously relevant field. So clearly if phi q is large, it means that the effective field is large, and vice versa. But now we want to look at it together with the relevant field that we have. So in the XY model, it's the temperature that we are varying, and by looking at the bin accumulant, we can detect the phase transition and characterize the phases. So now we can look at a two-dimensional diagram where we plot the bin accumulant on the x-axis, and this phi, in this case it's phi 6 for the Q = 6 model, on this axis, and then we can identify the fixed points not in the space of the fields, but in the space of the observables that are conjugate to basically to the scaling fields. So we do something which is very natural in Monte Carlo, not look at some abstract scaling fields if you do coarse graining theoretically, but actually look at the consequences of those fields. But as a function of what? Well, as a function of system size. So since everything happens very close to the edges here, it's a bit hard to see, but this is a blow up of this region here, well, this region here. So you see, if we do a small system size, well, we do L equals 2, 3, 4, 5. As we increase the system size, that's the same as increasing the length scale or lowering the energy. So that's similar to what's done in RG. But then we are measuring the physical observables phi 6 and u, and we just make a point for each case we do. So then we see, if we sit exactly at the critical point, then we flow to this point here, which is also shown here. So this is the universal value of the bin accumulant at the XY transition, which is 0.7 something. If we are in the ordered XY phase, we would flow to u = 1, and phi 6 is 0. That's the Nambu-Goldstone fixed point. And at high temperatures, we eventually flow the bin accumulant to 0, and phi 6 also will be 0, because in the high temperature phase, the clock field is irrelevant. Okay, but then we have this other point here in the clock model, which is where phi 6 flows to 1, meaning that this histogram becomes completely 6 the delta functions in this case, which we always do eventually in the ordered phase when the system size goes to infinity. Eventually we will flow there. But you see that if we are close to the critical point, we can actually get quite close to this Nambu-Goldstone fixed point before we cross over. Okay, so in this paper we basically show that we can explain all these RG flows with a scaling function with two relevant arguments, but I'm not going to talk about that now. Actually, now I'm going to show a very nice picture from the Okubo et al. Paper, because it turns out to just extract this exponent nu prime that governs psi. You can just do conventional finite size scaling in the region where this phi 6 becomes large. So this is what they did here, Tc minus T times L to 1 over nu, and then you just, if you don't know nu prime, you just adjust it until you get data collapse, and then you get the value. Okay, so I will talk more about this on Monday, but the main point, which is, I want to show it here because we are doing something similar for the JQ model, but maybe people are a bit suspicious about that because it's not the conventional way to do it. So now we write this phi q as some power of the system size. And what's the power? Well, it's the scaling dimension of the irrelevant perturbation. So yq is a negative number. And then it's a function which has two relevant, two arguments which are both proportional to delta, the distance from the critical point. So this is not normally how people do this in RG, because people say, well, the second length scale corresponds to an irrelevant argument, so they just write down the irrelevant scaling field here. But actually, with only that, it's impossible to describe this kind of flow. So we think it's very natural to also put in the second relevant scaling field here, which is driven by the same physical tuning knob, in this case temperature. But the thing is, this yq here and this nu prime q here, they are related to each other. And there's a lot of physics in how these are related to each other. So that's one thing, and that's actually one thing that had been very controversial, discussed in this paper, papers before and papers after as well, how nu prime and yq are related to each other. And I will talk more about that on Monday. But the point is that we can actually describe these flows with this kind of function, and this is what we also want to do with the JQ model. We want to investigate the emergent U1 symmetry in the JQ model in this similar way. So again, at the deconfined critical point, in the field theory language, the VBS is caused by condensation of topological defects. But the topological defects are irrelevant at the critical point. So in that sense, they are also dangerously irrelevant, similar to the clock perturbation. The clock perturbation is irrelevant at the critical point, but relevant in the ordered phase, and it causes the discrete symmetry breaking. Here, the topological defects cause the discrete symmetry breaking, which could be of this type or that type. But in the same way, there will be some RG flow diagram like this, where if you just study the theory without the topological defects, you would actually flow to a U1 spin liquid. But because of the topological defects, eventually you will actually flow to this VBS, which is like the clock phase. Okay, so the theory doesn't actually describe this thing, but it's understood that this would happen if you have a more complete theory. But if you want to describe the critical point, it doesn't matter because these topological defects are actually irrelevant there. So now we can also do with the JQ model, as we do for the clock model, we can calculate dx and dy, we can extract an angle, and we can make this kind of RG flows. So this is not published yet, this is ongoing work, but you see it's, as we did in the clock model, we used the bin accumulant to characterize the phases and the critical point, something that senses the relevant scaling field. But now we have two ordered phases, so we do the bind-accumulant difference. We have the bind-accumulant for the dimer order and for the spin order or magnetic order, and we take the difference. So in the Nel phase, we will flow to this point here. If we had a Nambu-Goldstone point, we would flow there, but actually we flow up to this d4 equals 1, like in the clock model, because because we have a dangerously irrelevant perturbation, which by the way is caused by the lattice itself. It's the lattice that dictates that we get this fourfold symmetry of the VBS. So we cannot, like in the clock model, you can just decide to study the model without the clock term, for example. Then you can just study the pure critical theory, for example. But in this case, in the JQ model, we cannot tune away the lattice, right? So we always have the perturbation in our system, and we always get this thing. This is in the JQ3 model. In the JQ2 model, it's actually a bit hard to see that turn up because the system has to be much larger.
Excuse me,
Yeah.
I have a question. Is this figure the result of the parameter JQ?
No, this is the JQ3 SU2 model, yeah, not the planar, yeah. Right. Okay, so in the same way as we did for the clock model, one can analyze various things here. This is work in progress, and I will show some preliminary results. I will basically show how to analyze this part to get new prime, which we also, by the way, had done before in collaboration with Naoki and Lo Jie. We had basically done already the same thing. It was just that at that time we did not fully understand what we are doing. Maybe Naoki will agree with me that we did something, but we did not completely understand. So we actually made some tiny mistake which maybe affected some values that we extracted. So now because of the work on the clock model, we know more what we are doing. So here I will just flash some results. So these are the unscaled results in the regime where this phi4 becomes large. We can do data collapse, but we can also analyze in some other way where we just look at where the curves. So these are curves for different values of j over q actually. Q is 1. And extract the exponents by line fitting instead of adjusting something here, but it basically is the same thing. But we did it in two different ways. We did the SSE at beta proportional to L. Why this strange number here? Well, this is basically 1 over the velocity. We determined the velocity in the paper with Suva before. So it's useful to basically scale it as L divided by the velocity. It doesn't really matter, but we also did it in the t equals 0 limit with projector QMC, and we get actually very similar results. So we get that this new prime, since it's still preliminary, we haven't really put error bars or anything, but I still want to show something. So it's basically a little bit less than 1 is what we think. New prime. In the old paper with Naoki, we get something like 0.8 or something like that. Okay. So, and now it turns out that this value is very important because we believe that it's not something that only affects this second length scale and so on. We believe, and this was introduced in this paper here, that this has the existence of this second length scale has some other more important consequences. So, the main point is that we have two length scales that are. So delta is the distance from the critical point, and these values of the exponents, we now roughly know what they are. So normally when you do finite size scaling, you take some observable which has some scaling form in the thermodynamic limit, so kappa is just one of the critical exponents depending on what A is. And then, okay, now I write down something with two arguments, but in the conventional scenario, you would really not even have the second argument, but I just put it here anyway. But basically for a finite size, you have some power of the system size times this scaling function. Now, this finite size scaling form has to be compatible with the thermodynamic limit. So how do you accomplish that? Well, the scaling function itself must take the form of a power law of its argument such that you cancel out all the L dependence and you get that correct power of delta. And of course you do that if this f goes to the first argument to the power kappa. Then you cancel out the L dependence and instead you get delta to the kappa. So that's how finite size scaling and the thermodynamic limit are connected in the conventional way of thinking.
Excuse me,
Yeah.
I have a question about the nature of the quantity A.
Yeah.
I'm talking about the quantity which is supposed to be zero when this symmetry breaking field is zero.
Yeah, so for example, I think this could be anything. It could be also divergent quantity if kappa is negative, right? But it could be, the magnetization below Tc in an Ising model, for example, then kappa is beta.
Yes, but my question is, I think this form may depend on the nature of the A. Whether A is insensitive to this symmetry breaking field or what.
Oh, right. Yeah. So it should be a quantity which has some, power law dependence. But I think beyond that, it should be true for any. All the quantities we look at normally at the critical point, they just behave as powers of the system size, right? And then if you go away from the critical point, you have this kind of scaling function of this argument. So I think this is quite general, but we can discuss it more after. Okay, but the point is that there's a very well-defined way that the scaling function has to behave in order to reproduce the thermodynamic limit. In our alternative scenario, since we have two scaling arguments, it's not so clear if you don't know anything more. If you only know, okay, I have a scaling function of two arguments, what happens when L becomes large? So let's say delta is small but finite, and L becomes large. That's how you take the thermodynamic limit, like we did here. But which argument of the scaling function will actually matter here? Will it be the second one or the first one? So if, for some reason that we don't know, but we are just posing this as something that seems to work, that the function goes to the second argument to the power kappa, well, then we get the correct delta to the kappa. But then to cancel the L dependence, we have to have a different prefactor from before. We have to have nu prime instead of nu in the L dependence to get rid of the L dependence. So why are we proposing this? Well, because we have some problems in the finite size scaling that cannot be described by the conventional scenario. So then we are thinking, okay, what is the way around that? Another way, equivalent way to look at it is, okay, to get finite size scaling at the critical point, we can just write our quantity as a function of the correlation length. So for example, in this way, since correlation length is delta to minus nu, I can invert that and say that A is correlation length to minus kappa over nu. And then what we do in the conventional finite size scaling, if we are at or very close to the critical point, we just replace psi by L and then we get that. But in our alternative way, it's actually psi prime that should be replaced by L. And when psi prime is L, then the normal correlation length is L to nu over nu prime. This is not so clear here, I think, but it's not my fault. It's Keynote has this weird problem sometimes. L nu over nu prime. So then we get A is L minus kappa over nu prime. So it's not so crazy, I think, if you think, okay, you approach the critical point, you have some two length scales diverge, and then the longer one reaches the system size, then we are saying, well, then the shorter one has to stop diverging. Well, apparently that's not happening in the clock model, because actually in the clock model, the first scenario is actually still valid. But apparently in the JQ model, this looks like it's so. So you can basically think of it as, okay, replacing correlation length not by L, but by L to nu of a nu prime. Then we get some modified scaling laws. So for example, the spin stiffness, this is the conventional scaling form of the stiffness at criticality, and in this case we are dealing with Z equals 1 and D equals 2, so this is just 1 over L. In our modified way, we get the exponent modified by nu over nu prime. So implicitly, people always assume that this second argument doesn't matter, or actually people never even talked about putting in a second argument. There was belief that the dangerously irrelevant perturbation, since it's irrelevant, it just causes some scaling corrections. But in our scenario, it actually modifies the finite size prefactor. So it's a finite size effect, because we are not changing the thermodynamic limit. We are saying that the finite size behavior can change. So now we can say, okay, will this work? Because we know nu is around 0.45, and let's say nu prime is around 0.98. Okay, there's some uncertainty still in this number because we're still working on it. So what I'm showing now is quite preliminary, but still it's quite... we had some results already in that science paper, but now we are working on much bigger systems, and we are checking things more carefully, so I will show those results. So nu over nu prime is about 0.46 now. Okay, so this has actually been going on for some time, just for curiosity. Okay, running for about 2 years, since we don't have a K computer, unfortunately. Maybe in the K computer this would be running 2 weeks or something, I don't know, but we have to struggle and use 10 or 20 million CPU hours on the clusters at Boston University. But still we were able to do L up to 512, which is much bigger than we did before. So this is some example of what we do now. So this is for L256, it's the bin accumulant for the dimer order and the spin order. And it turns out that now we think the best way is to actually analyze the crossing points, for the same size, different accumulant. And that actually gives a critical point estimate which is completely monotonic, unlike this L2L estimators that I told you about before. So we believe now the critical point is very close to 0.0451. So for what I'm showing next, we will take that as the critical value. Okay, we can look at the slopes of the bin accumulants. They again give, so this is just the derivative, but evaluated now at the infinite size critical point. That should grow with the system size as L to 1 over nu. These are some examples. So you see that the slopes have a peak close to the critical point, but now we'll just look at it at the critical value. And then we get some behaviors which can be fitted very nicely to power law with one correction. And this agrees almost perfectly with what we have in the science paper based on much smaller sizes. There the biggest size was 160, now it's 5. Actually here we do 448, the 512 has a too big an error bar to matter, so we didn't include that here. We still need to improve the last part. But in any case, and the correction exponent is also quite reasonable here. So that value of nu that we had before seems very stable. Okay, now maybe the most crucial quantity, the spin stiffness and uniform susceptibility, which, as I told you before, is where people first started to notice that something strange is going on. This is what people are the most suspicious about. They should actually scale in the same way. And you see that they do. There's just some difference in amplitude. Okay, so now this is what we predict. So in the conventional scenario, they should decay like 1 over L. They actually decay much slower than 1 over L. What we believe is that we should have nu over nu prime there. And actually, this is what we had for nu over nu prime, and this is what I put in here in these fits. And the correction exponent is quite reasonable. It seems to work, very, very well. Okay, how about the correlation functions that we get to need to extract the exponent eta, which is quite an important exponent. So in the conventional view, this is what how you deal with correlation functions. So you say, okay, if the distance is much less than the system size, but still, of course, large, then the correlations should decay. If d is 2 and z is 1, they should decay like 1 over r to 1 plus eta. So from that we can extract eta. But now if we have finite size, that is modified by a scaling function of r divided by L. And often we actually look at the distance r equals, the maximum, which is L divided by 2 or L divided by 2 times square root of 2 or something like that. So if we look at this form and then we take r goes to L, then we have to eliminate the r dependence, and instead it should just depend on L. That we get if the function is a power of r divided by L and the power is 1 plus eta, so then we get L to minus 1 plus 8 instead of r there. Okay, that's the normal way of doing it. We can look at the longest distance as a function of system size. Or we can look at r much less than L. We should get the same power. Okay, this is what we get here. For an example of the spin correlation function on 2 different system sizes, and this is from this projector QMC. Okay, so it's the red is the bigger size, the black is the smaller, and green weight of moment. Okay, so now you see that if we want to have r much less than L, it's not so easy to see where we should do the fit. But this has actually also been done before on even slightly bigger system sizes in a 3D loop model, which is an alternative way to simulate the deconfined critical point by Nahum et al. They argued that doing it this way, they get eta around 0.3, which is very consistent with what we see here. But then they also noticed something that we also see here, that if we look at the largest distance, that's the green point, so r equals L divided by 2. Well, over here it looks like the decay is sort of similar, but then for the bigger sizes, you see that the decay starts to go slower here. So it looks like it's actually not consistent with this. Well, of course, this fit here, you may say, also is not done in the correct place. Maybe one should actually fit it at larger r, but then we have these boundary effects, so it's not so easy even to do it. But in any case, what happens if you look at the largest distance, you will find actually the same problem that Kawashima and collaborators did before, namely that eta starts to become negative actually, which is not good news for a conformal field theory. But then we have our new scenario, because in our new scenario, I just do the quickest way here, which is just to say, okay, instead of L, we should use L nu over nu prime. Then the correlation function at the largest distance should actually not be decaying with 1 plus eta, but 1 plus eta times nu over nu prime. So then if we analyze that behavior, eta may actually not be negative, because we are not actually seeing 1 plus eta, we are seeing something else. So this is what is shown here. So now I show both spin and dimer correlations. And actually these are the squared order parameters, which are basically the space integrated correlation functions. So they have the same power laws as the long distance correlation functions. So we can fit it to this form, but the power is 0.6, which conventionally would say that eta is minus 0.4, which is not good. But actually, in our modified scenario, if you solve for this, you see that eta is around 0.3, which is actually okay. So it seems to work also there. And just to, it's also useful when you look at the correlations to also plot them versus 1 over L on a linear scale, just to see, make sure that it doesn't look like they go to some non-zero value, because that would be what it does at the first order transition. At the first order transition, these should scale to some non-zero values again, because you have coexistence of the ordered and disordered phases. Well, of course one can argue that the systems are not big enough and blah blah blah, but at least with the fit we did and the way it roughly looks, it's at least plausible that it vanishes, right? So it's at least not some obviously first order transition. Okay, now this eta is also interesting because people have actually been talking about emergent SO5 symmetry in these kinds of at the deconfined critical points. So there's a special theory for SU2 where you have actually emergent SO5 symmetry. And people have seen that in these 3D loop models that I mentioned before. People saw some evidence of SO5 symmetry in the order parameter. Okay, so one requirement to have SO5 is that these exponents, eta for spin and dimer, should really be the same. And the results by Nahum et al. Actually within error bars they are the same, but the error bars are pretty big. So one way to test this more directly is to take the ratio of the two order parameters and see how that scales. And okay, now it's not so easy to see, but you see this is a log-log plot actually, but on the y-axis this is almost constant, but it's not really constant, and you can actually fit it to something which is slowly divergent with a power 0.02, and there's a correction here as well. And I didn't plot error bars here, but you can see from the scatter what the error bars is. So I would say that it looks like the eta exponents are not really the same, but you know it's not completely conclusive maybe, because you could say, well, eventually they become the same. But I would say most likely they are not the same. And actually, it's good news if they are not the same, because this conformal bootstrap method has been used to attack this problem too. So you know, if you do conformal bootstrap for SO5, then people have found that that puts a condition on the exponent eta, that eta has to be larger than 0.6 or something like that. Otherwise, yeah, that's just a condition if you have SO5 symmetry. Since our eta seem to be around 0.3, it would not be consistent with the conformal bootstrap. But if you don't have the SO5 symmetry, then we are actually okay. So I would say that at least this looks like we may not have SO5 symmetry. Okay, so I think my 2 hours have gone, so let's I just, as the summary, I put the same as my outline for what the main points are. So you see I have shown you large-scale results and discussed the emergent U1 symmetry and these 2 length scales that, you know, if you really write down these scaling functions with 2 arguments, it looks like you can explain everything. But one thing here which I want to stress is that the fact that we look at these scaling functions with 2 arguments and we look at the limit when L goes to infinity and so on, it actually implies, since we are looking at things like the spin stiffness, which is a property of the Nell state, it actually implies that this length scale psi prime, which is governed by the exponent mu prime, also must exist in some way in the Nell state. It's not something that exists only on in the VBS state, which is what people said before. They said, well, the dangerously relevant operator is something related to, you know, this discrete symmetry breaking. It's something in the VBS state, but we don't need to worry about it in the Nell state. But actually, we think that we have to that length scale is reflected to the other side of the critical point, and we have a candidate for it, namely the pi zero triplet mode, which actually is gapped in the Nell state and becomes gapless in the deconfined critical point. Maybe that actually scales with this exponent. Well, this is something we are checking now in the work with Maro. Suva, we checked that a little bit before, but I would say our results were not really conclusive. Okay, so now very quickly I will show 3 more slides, if I may, like half minute each. because we have 3 recent works that all are in some way related to this work. So the first one is related to this pi zero mode, pi zero triplet. So it turns out that, you know, for a long time people have known that in the 2D Heisenberg model, without anything else, there's actually an anomaly. So, you know, we know that the low energy excitations are spin waves, but at high energy, especially at q equals pi zero, there's some anomalous depression of the excitation energy, which actually is seen experimentally and in many studies of the Heisenberg model as well. So this is a figure from this paper which actually argues that the excitations close to pi zero are fractionalized spin-on excitations in this material. Now in our paper from a couple of years back, we did quantum Monte Carlo and analytic continuation and some effective modeling, and we were able to basically match the experimental results perfectly when we put in the experimental broadening. Here it's not so clear, but the point is that at pi zero compared to pi over 2, pi over 2, there's much more continuum, and also the excitation energy is a little bit lower, which it should not be within spin wave theory. We think that's exactly a precursor to what happens at the deconfined critical point, where actually the pi zero mode becomes gapless. So when we, in our paper, did the JQ model, as we did with Marvel Suva before also, we could see that, you know, the excitation energy is depressed and eventually vanishes, but it's already a little bit depressed in the Heisenberg model. You don't see it clearly in this picture because of the scales, but if you look here. So we think that's a precursor to deconfined critical point that we actually see in the material. The other paper I want to mention is that we have done a JQ model defined on the checkerboard lattice. We've only put the Q term on every second plaquette. And then we have actually not a columnar VBS anymore, but we have what's called a plaquette singlet solid, which is a twofold degenerate state, so you can form strong singlet on every second of those Q terms. So it's a twofold degenerate state. And there we actually found a first order transition between the null state and that appears to be associated with an O4 symmetry, which is basically combining the plaquette singlet, which is an Ising order parameter, with the O3 AFM and combining that to a 4-dimensional vector. We don't know for sure if that's something that really implies up to infinite length scale, or if there's a length scale governing where the symmetry is eventually violated. But in any case, we saw that up to very large system sizes, and we think this may actually be of relevance to strontium copper borate, where there is actually such a state. Okay, the last one I want to mention is work in collaboration again with Wei Xiao and Wenan Guo, and Wenan's former student, who is now my postdoc in Beijing, and Yu Cheng Lin in Taiwan. We have looked at disorder in the JQ model, and there we believe that we have found something that people have looked for quite some time, the so-called random singlet state. So you can see when we put disorder, this is just an example from an actual simulation. The VBS is actually broken up into domains, and where domain walls meet in a certain way, there are actually spin-ons, localized spin-ons. There's actually a spin-on here, for example. And those spin-ons will form a subset which has some interesting magnetic properties. And we find that it's actually a critical state which has some well-defined critical exponents and a varying dynamic exponent, and it's quite exciting what's going on. And we even think that there may be an experimental realization in a material that people have started to look at quite recently, which is actually a random J1, J2 Heisenberg model, where on some plaquettes, depending on what you have inside the plaquette, you have a J1 interaction or a J2 interaction, and now those appear in a random way. And we have some analysis of their experimental results which look very similar to what we have in this model. Okay, that's it. Thank you very much for bearing with me for 2 hours.
Thank you. Any question?
I have a question about interaction and spin at the critical point.
Mhm.
Do you expect kind of the power decay interaction with spinors?
Are you talking about the random system or in the clean system?
Maybe both.
Okay, so in the clean system at the deconfined critical point, the spinors are strictly speaking not completely free because they are actually coupled to, in the theory at least, they are coupled to this U1 gauge field. But apparently that coupling effectively is very small because we have some work where we were able to model the critical state as a gas of non-interacting spinons. And I think in the theory, okay, you can write down the field theory, so in some sense you know how they are coupled, but effectively in the strongly interacting system that you cannot solve, I don't think people know exactly what the effective spin-on interaction is. But maybe it's some sort of logarithmic thing because the spinors are also like vortices.
So there is no prediction from the theory argument.
I don't really think so. Yeah, I remember I discussed this with Sentil, but yeah, it was not really quite clear what he was telling me. But maybe they know, but it's hard to sometimes get out the answer. In this case, we also really don't know exactly how the spinors interact with each other, but we just know what kind of magnetic subsystem they form.
I don't quite understand why the second length scale must exist also in the antiferromagnets.
Right.
So it's based on the scaling of the ms squared.
Yeah, it's basically the way we.
So then it's okay. Yeah.
Right.
But in that case, the data should be common for antiferromagnet phase and the VP space.
No, we think that they are not common. So in the
They should be
SO5 case, they are, common. But as I said, it's not completely conclusive. But the point is, if we look as a function of J over Q.
But how about the sigma? So sigma, you said it's about 0.6 for both phases, right?
Yeah. So they are close to each other, right? So the sigma, which is 1 plus 8 nu over nu prime, that was around 0.6. So so eta S is approximately equal to eta D. But the difference is very small, that's why it's hard to see. but let me, just since you asked about this, this is the AFM state and this is the VBS state. So in the VBS state, okay, what are the energy scales? There's a gap, a triplet gap, and that should scale as the distance from the critical point to the exponent nu. I guess it's nu z, but z is 1. Okay, then we should have this other u1 length scale, which you can also associate with a singlet gap, which should be given by this other exponent. Okay, on this side, what energy scales do we have here? Well, here we have the spin stiffness. That should go like delta to, oh sorry, this is not minus, this is plus, right? I wrote down the lengths instead of it. This should have a scale with the exponent nu. Again, it should be nu z, but z is 1, so it has to be there. Okay, so this is what people normally would say, that okay, this nu prime scale only exists here. But basically, our arguments involve some quantities that are defined on this side, like the spin stiffness. And then we make an argument of sitting somewhere here and letting L go to infinity. And that's how we argue that nu prime appears. So that means that nu prime must exist on this side as well. So there is something, let me put a question mark, which also goes like delta. new prime here. And I think it's not so strange that it does that, because at critical point there's often things that appear on both sides. So for example, you know, in this side we also have the Higgs, the amplitude mode. Okay, the amplitude mode also scales with nu here. And there's an exact relationship between the Higgs mode on this side and this triplet gap. It's something like square root of 3 times triplet. I mean, they're really almost exactly the same. So maybe this length scale also is somehow reflected here. And again, what could it be? Maybe this could be the pi zero, the pi zero triplet gap that I talked about. We are trying to check that, or maybe it's something else. But it seems like, and I think that's an important physical insight if what we are saying is actually true, that one cannot neglect that length scale.
I have a question about the symmetry enhanced first order transitional
Yeah.
topological model.
Yeah.
If this is true, this may result from the topological sample.
Yeah. So Ribu Kaul, who is not here yet, but he maybe is just about to arrive.
Yes,
He also has some work on a different model and a different enhanced symmetry, but he argues that there could be some topological term in the field theory which really enforces this as an exact symmetry.
Is there any field theoretical analysis to explain or support this phenomenon?
Well, apart from his work, which is basically a proposal, I don't think he has really analyzed it. I don't think that there is anything yet. And actually, I discussed it a lot with Chenka Xu and Subi Sachdev, Sentil, and others. And first, for example, Subi Sachdev first, he said he doesn't believe it. And then at some point, he sent me an email saying, I think what you're saying is possible. But I he didn't say, say in which way it was possible. But I think it's a very good question to think about how that could happen. Maybe when Ribu comes here, we can talk to him. Yeah.
If there's no further question, let's thank the speaker.